So, good afternoon one and all present here. Welcome to this KWK talk. I request our director of JNP, Dr. B.R. Guruprasad, to welcome you all.
Respected speaker of today, Professor Indira Chatterji, faculty and other officials from ICTS, my dear students, good afternoon to all of you and welcome you all to this KAAPI with Curiosity lecture jointly organized by ICTS and JNP every month. And today we have a very interesting topic, Hyperbolicity by Professor Indira Chatterji from Côte d'Azur from Nice. When I was looking at her profile, I told her really the places where she had her education as well as she worked really made me envy some of the best places, and I'm sure that she has been inspired by those places to look into the workings of nature through the language of science, mathematics. So without intervening too much, now I request Sharanya to announce the next thing. Once again, welcome you all to this KAAPI with Curiosity talk, and welcome to you, ma'am. Thank you.
Thank you, sir. I request Professor Samuel from ICTS to introduce the speaker.
Yeah, friends, it's a pleasure for me to introduce our speaker today, Indira Chatterji from Nice in France. She's a professor of mathematics. And this lecture is jointly run by the ICTS in Bangalore as well as the Planetarium. It's a joint venture to reach science and mathematics to the public. So before I start, let me say a few words about ICTS. So in ICTS, we're involved in three different kinds of activities. The first is scientific research, and we conduct research in mathematics, physics, computer science, and some physical biology. The second aspect of the work is in programs, and programs are a way of holding meetings where different people come together from all over the world or all over the country to discuss very specialized topics. So, for example, right now there's a program going on in hyperbolic geometry, and that's exactly what brings Indira here to Bangalore. And earlier this year, just last month, we had a program on two programs, one for women in mathematics and another for women in physics. And I can see some women in physics from last year's, some alumni of last year's Women in Physics program right here. I'm glad it's working. We're attracting women into the sciences.
Also this year.
Sorry, also?
This year.
Also from this year, yes. And finally, we have outreach programs. So this is an example of the outreach programs that we are trying to use to get people interested in science. And that outreach extends throughout all ages. For example, we have school children and graduates at the bachelor's level, master's level, and also the general public, trying to get people interested in science so that we can promote the ideas of rational thinking in the population. So yesterday we had a math circle at the Raman Research Institute, which is trying to get school children interested in mathematics, and Yamuna has been involved with that as well. And this coming Saturday, we have another event. It's called a PRISM event about physics, trying to get school children interested in physics. So just take a look at our website and see what events interest you and see if you can find something you'd like to attend. So coming to our speaker today, Indira Chatterji is a professor of mathematics at Nice, and her interests are in low-dimensional geometry, like 2 and 3 dimensions. I mean, 2 is quite old, but 3-dimensional geometry is a very vibrant subject. And also in the topology in group theory, geometric group theory. Those are her interests in mathematics. Apart from her interests in her research interests, she's also very involved in popularizing science, and she animates art pictures to put across mathematical ideas to a general audience. And she's also interested in the struggles of women to find their rightful place in the world of science and math. That's one of her interests. And today she'll be talking about hyperbolic geometry, which is a very new and strange kind of geometry. It's not very new in the sense it's about 100 years old, but there's still research going on in it. In school, you would have learned about Euclidean geometry, where if you take a triangle, you can scale it up to any size without changing its shape. You can find similar figures of any size. Now, hyperbolic geometry is quite different from this. In ordinary Euclidean geometry, you can make a figure on a table, and many architects and town planners do this. They have a map on a table or a floor plan of a building on a table, and they scale it up to any size, and you can build it exactly to scale. This is a feature that does not work in hyperbolic geometry. When you scale up a figure, it gets distorted. And I can see some examples, you can see some examples of hyperbolic geometry right here on the table, concocted by this young man whom I just met a few minutes ago. So our speaker today will help you to come to terms with this new kind of geometry. And I must also add that hyperbolic geometry has had a huge impact in physics. And also it has inspired people to, like Escher, in art. And it's a huge effort of human imagination to comprehend geometries like this. And this is exactly what Indira is very skilled at. And she'll lead us into this brave new world of hyperbolic geometry. Indira?
I have a bucket. Thanks a lot for this very nice introduction. Do you hear me well? Okay. So thank you very much for this opportunity. I'm very happy to be here. And I don't very often give talks for such a wide audience. Usually my audience is wannabe aspiring mathematicians or very young mathematicians. Here you are very young, maybe mathematicians, hopefully mathematicians. So anyway, if you have any question, please feel free to ask or keep your questions for later. And I've been told once that, I think it's von Neumann who said that you never really understand the math, but you get used to it. So I hope that those pictures will help you get used to new concepts. So I'm starting with this cartoon. Have you ever seen this cartoon? This was a cartoon I used to watch when I was a kid, and it was all drawn from a line, and to this person, all sorts of things happened, and the geometry that I'm going to be looking at today is a geometry where if you take a large ball and you try to project this ball on a line, you'll have, the projection will go through some kind of, to some kind of a narrow point. You will not have arbitrary large projection no matter where your ball is. But this is really to make the link with my cartoon. So I'm going to start with a few definitions because this is what math is about. We need to, this is in fact what I really like about math, is that we agree on some definitions and then we build from there. And so today the most important definition is going to be a metric space. So it's a set with a distance, a way to measure the distance between any 2 points. And so this distance has some features, which is the only way to get zero distance between 2 points if it's the same points. You don't have two different points at distance 0, and two different points have a distance that is greater than 0. The distance between x and y is the same as the distance between y and x. So this, when you think in terms of distance, well, we'll see. So this is my definition of distance. It may not be yours because you know that if you want to go from some place to the top of a mountain, it's not the same as going from the top of the mountain to downhill. But today, my definition will be so-called symmetric, And yeah, and the third point is the triangle inequality, which is that you take 2 points, and if you make a stop in between, it's going to be longer. There's no shortcut by making a stop in between. Right. So you can put several metric on the same space. So here you might recognize the space. It's your city. It's Bengaluru. So if you try to go from the ICTS, which is where I am, to here, if you use a car, then that'll take some 40 minutes if you're lucky. But if you walk, that's going to take much longer. So the metric of a car driver is not the same as the metric of a pedestrian. Whereas the metric of a pedestrian is more likely to be symmetric. The metric of a car driver, if you go and come back not at the same time, the distance is not going to be symmetric. But for today, my distance are symmetric. All right, so that was an example of a metric space. So we're going to be looking first at several examples of metric spaces, and then we're going to see what is hyperbolicity in the context of metric spaces. Another very important example of metric spaces are graphs. And so graph is going to be a set of vertices, which are points, and you want edges that link 2 points. So here my graphs, with the definition I gave, are simplicial, meaning that there is only one edge in between 2 points, but you could imagine graphs with more edges. And I'm going to call it connected if you can go from any one point to any other point. So graphs are everywhere. The graphs are a very convenient way of modeling life. For instance, Facebook, right? You've heard, maybe the young people don't know Facebook, but the older people like me will know Facebook. So Facebook can be represented with a graph where the vertices are the people, and you put a connection in between two vertices if those people are connected on Facebook. So that's typically one example of a graph, but there is many more ways in which we use graphs to model real life phenomena. So, and the graph is going to be a very useful example of metric spaces, because you can measure the points in between, the distance in between 2 points just by measuring the length of a path. Maybe I have that on my, yeah. So here are a few examples of graphs. So the first one is the graph that I commonly associate to the integers. Here I didn't put the numbers, but if I link two integers, if their difference is 1, I'm going to get this graph. The graph just below is the graph that you would get from the integers z2, the couple of integers. You have many more graphs. Graph theory is a very interesting field that is kind of in between, commonly studied in between computer science and math. All right, so yeah, that's what I was saying. The set of vertices of a connected graph form a metric space, and really you measure the distance by just the length of a path between 2 points. And here comes another very important definition that I'm going to be using today, is the notion of geodesic. So if you have a metric space, you have a way of measuring the distance between 2 points, and you want to know that there's a path realizing this distance. So geodesic can be thought of as a generalization of straight line, because if you're in the plane, if you're in the world, we used to know that the shortest distance between any 2 points is a straight line, but this is in our word, in our metric. If you change the metric, you might have other geodesics, and we'll see that. Oh no, did I do something wrong? I did something wrong. Yes, okay. All right, so another thing you might want to look at in a metric space is the diameter, which is how far what is the distance between 2 points that are furthest apart? So you can have finite or infinite diameter. Before the graph I showed you with the little points, they had infinite diameters. But to be honest, we humans are not that good at understanding infinity because we're in a finite kind of world. So we only ever see finite things. We have to imagine infinity. Right, so let's look at examples now. The first example is the plane, which we call R2, with what we call the Euclidean metric. So if you have 2 points, this is the formula. Right, this is the formula on which you compute the metric, and geodesic is a straight line, and you can also draw a ball, which is a set of points that are at a distance smaller than some number to a point, and the balls look round. Now, if you change your metric to what I call the New York metric, or actually any modern American city will have this type of metric, it's a metric that's given by a grid, right, and you can use it. You can have this formula. You express it with this formula, but then when you want to go from this point here to this point here, any path here will do. Anything that doesn't backtrack will realize the distance. And here balls look like squares. So there's another metric which we call, since I work in France, that's a metric I know, it's what we call the French railways metric. So why is it? Because if you want to go from one place to another in France, you have to go through Paris, because all train tends to go to Paris. So you have to take your train, go to Paris, hopefully not get stuck in a strike or something, and then take your train to go wherever you want. So all the, I said most paths because if you're really on the same train line, you're going to stop wherever you need to stop. But this means that the distance gets quite distorted. You know, you think that you're close, but in fact you're not, because you have to go to Paris before going to your place you want to go. So this is another metric you can put. And another one that I like to describe is the tourist metric. So when you're a tourist somewhere, you're in a city you don't know, there's a road that you're going to know better than the others. The touristic road, this is where people send you. So what you're going to do when you're in a new city, as a tourist, what you do is you always go back to the road where you know how it is, and then you go from there, and you go up and down, and then you go from there. So that gives a whole different distance. All right. So those are some examples of metrics you can put on the plane. So the plane I call R2. The plane is something infinite. So it's as big as you want. And here I'm giving you a small picture of what I can draw on my piece of paper. Right, so there's some metric spaces that are non-geodesic. So here I drew a sphere, which is a set of points of length, of Euclidean length 1 in the space. And so if you think of a hollow sphere, and you measure the distance between 2 points, you have 2 ways of measuring the distance. You can remember that your space R3 and measure the distance like this, but then your shortest path, if you're, say, a human on the sphere, it has to remain on the sphere because you can't cut through. So the shortest path is not going to realize the distance, meaning that this is a metric space that's non-geodesic, because the geodesics do not, the shortest path do not realize the distance. So I'm going to be looking at spaces where shortest path realize the distance. Right. So how to decide to try and study the geometry of a space, I can look at geodesics, but one thing I'll be looking at today is triangles. And my definition of triangle today doesn't involve angles, which is kind of bizarre, but a triangle in a geodesic metric space is just going to be the data of 3 points and 3 geodesic. 3 points and 3 shortest path. And this is these are the objects that I'm going to study today in order to understand my space. So yeah, as I said, I didn't define angle now, but we'll see angles later, and we'll see how they relate to this notion of triangle, which doesn't have angle. So now I come to the definition, which is the title of my talk. And so for this type of metric spaces, if you're in a graph, for instance, you don't necessarily have the notion of angle. You don't know how to define, even in the Euclidean place, it's actually pretty difficult to understand what an angle is. Because to understand what an angle is, you need to have geodesics, and then you need to, it's tricky. So we're not going to talk about that today. Oh no, wait, okay. This is, okay, so I'm going the metric space is going to be called hyperbolic for today. Mathematicians tend to call delta hyperbolic, and also they have a little fight on how we should call those spaces, because there's some purists that say that no, hyperbolic is the hyperbolic plane that I will be showing to you, and we should call delta hyperbolic. The definition that I'm giving you is that you can find a number so that all triangles are thin, which the triangles, I said, are 3 points and a choice of 3 geodesics, and thin means that any points on a side is a distance less than delta to another side. I'm going to show you a picture. Well, first, notice, if you have a finite graph, you have bounded diameter, so any triangle is going to be d-thin, where the thinness is the diameter. So if you want to think of hyperbolicity in a finite setting, you need to have a very large diameter and look at very thin triangles. But that's going to be for later. Now, hyperbolicity is a space in which triangles, large triangle, will look like this, meaning that if I take one side, here I'm doing here what I drew is the delta neighborhood of this side, so all points that are close to this side. And I do that with another side, and you can see that the third side here, which I drew in green, I don't know if, the third side is either close to this side. If I pick a point on the side, it's going to be either close to this side or close to this side. And this is something that does not happen on your piece of paper. If you're in R2, R3, or Rn, you take 3 points. If you take them really far apart, your triangle is going to be not thin, because suddenly those points here are going to get really arbitrarily far from, if you take this point here in the middle, it's far from here and it's far from here. And R2 with the New York metric, here I called taxicab metric, but is really a New York taxicab metric. So this with my definition, notice that this with my definition is a triangle, because there's 3 points, A, B, C, and 3 geodesic, and this is a geodesic for the taxicab metric. So this is a triangle, even though it doesn't look like a triangle. And you can see that it's not thin. This is a triangle as well. This is going to be thin, but the space is not hyperbolic because we want all triangles to be thin. But if you look at R2 with a tourist metric or with a French railway metric, but it's less nice, it will be thin. It will be hyperbolic. It will be even zero hyperbolic. It's what we mathematicians call an R tree, a real tree. And here you take 3 points, X, Y, Z, but your distance is going to be, your algorithm to move is go back to Broadway. This really is Broadway. Go back to Broadway and then go to wherever you need to go back to this street, go. So this gives you a thin triangle. All right, so now we're going to observe hyperbolicity, the phenomena of thin triangle. Where do I find it? So in graph theory, we call tree a graph with no loop. And this is always zero hyperbolic. Yes, here I drew a picture. Of course, you know, in India, we have banyan trees, and those are not exactly trees in this sense, but a tree in graph theory is a graph with no loop. So this is always zero hyperbolic, and here you can, in the real life, actually there are some predators, I forgot which one, there are some predators that actually know some feature of hyperbolicity, because, for instance, here you can see, I drew some ants, and if you're a predator, you know that you can wait for the ants here. They're going to have to go that way. Here's another way where you can observe hyperbolicity. It's underwater. So you have your two dolphins, they want to communicate. So they're going to emit a sound. The sound is a wave, and so the shortest path for the sound to go from one dolphin to another is to go down, because with increased pressure, the wave is going to have an easier time transmitting when there's more pressure. So when you're underwater, the pressure increases as you go down, so the sound will follow the path of most pressure and will take this route. It needs to go down. And so what is this route? What is the path of the sound that the sound is taking exactly? So I'm going to flip my dolphin because I want to stick to the mathematical model. And let's try and understand a two-dimensional version of this model. So this is where, you know, you do math. You stop caring about real life, and you're like, okay, real life resembles this picture. So let me just focus on this picture. So now what I'm showing you here is the upper half plane. So the upper half plane is the complex number with the real with positive reals. I mean, this is the complex plane, but what's upper is it's when the imaginary part is strictly positive. Okay, but here, think you're in R2. Think you're on a piece of paper, and there is a line which is a zero axis. I have 2 points, and I want to compute how the sound travels. So this is the straight line if you were in your Euclidean plane, but I told you that the sound needs to go up because of the pressure. So the way it goes up, it follows a circle which is perpendicular to the blue line. So how do I find the circle which is perpendicular to the blue line? I take a straight line between A and B, I do the perpendicular, and I see where it intersects, and this is the center of the circle, and I can draw my circle, and if I do that, I have those two straight angles. My circle intersect the blue line in a right angle. If I were to draw the tangent at the intersection, I would have something that's perpendicular to the blue line. And the distance I'm going to compute out of this, I'll give you this formula for the distance. So now I have computed, so here I have, this is dolphin A, and this is dolphin B, and this is how the sound moves from dolphin A to dolphin B. And mathematicians even have a formula for that. So how does the formula work? You're going to compute the distance between A and B by taking the log of the distance between B and A infinity, which is this piece, divided by this distance here, times this piece here, divided by this piece here. Right. So now you have to believe me that this actually, so this is a distance. I'm not going to do more math than that. This is as much math as we're going to do today. So this is the formula for the distance, and this gives this as geodesics. And then you can see that if you want to go from A to B, then in this case, if you're just right above the other, when the dolphin is right above the other, the geodesic is a straight line. And here you can see, but in general, so we have this formula, and now here I draw those two straight lines, and I'm going to see what happens when my two dolphins go really, really deep underwater. So here you can see that at infinity, the points A and B are getting, in fact, really close to each other. And you can see that from the formula because you're taking a log. And those two distances can become the same, so the log, this quotient tends to 1, and hence the log tends to 0. As A and B, as A and B go really far. And now if the dolphins go really close to the surface, this is this picture, then you can see that the distance between those two dolphins is going to tend to infinity. This is where the model, each time you go at infinity in your models become worse and worse and very far from the piece of reality you started with. And so this is what I'm going to call ideal triangle, which are triangles with vertices at infinity. So there is a map from the complex number to the complex numbers, mapping this map. This map will actually map all this upper half plane into the circles. And what's special about this map is that it will preserve the angles. So all the ways that we had to compute geodesics, we can push them in this disk model. So this is what we call the upper half plane model, and this is what we call the disk model for the hyperbolic plane. So what I described here with those formulas for the distance is the hyperbolic plane. And now, since I promised a space in which triangles have angles that sum to less than 180 degrees, here I drew a triangle. So how do you draw a triangle? You need to take 3 points and 3 geodesics. And I just told you how you can find the geodesics with circle that arrive perpendicularly to this circle. And here I can see my triangle, and you can see on the nose that it has the sum that's less than 180 degrees, because if you were to draw a flat triangle, you would have, all the angles would be bigger, and those are 180 degrees. And if you go to infinity and you look at your ideal triangles, you can see that the angle here is 0. So, all right. So another feature of the hyperbolic plane is if you take this point here and turn around, you will see more than 360 degrees. You will see more than 2 pi when turning around any point. And this is an important point. And if you want to play with the hyperbolic plane, there is on my former student's website, he has a little app where you can put in the points, it will compute geodesics, and it will compute neighborhood, and it will compute triangles. So you can, yeah. Right, so where does the terminology come from? Hyperbola is a set of points in the plane whose difference are pairwise distance to two fixed points. And so in higher dimension, so this is a hyperbola in dimension 2, but in higher dimension, you really see the pictures that have been, the models that I've been discussing. And here you see the geodesic, and here you see how you project. This is your hyperbola that we currently call hyperbola, and if you cut it by a plane and you project it down, you see the disk model that I've been discussing. All right, a little sewing digression, right? Because I promised that we'll see hyperbolicity in your clothes. So here's how you make here's how you don't make any more cheap t-shirts. We used to make cheap t-shirt that way. If you find like old stuff. So this is how you make a cheap t-shirt, because I'm saying cheap because it's labor cheap, because you only cut squares and rectangles. So what you're going to do, so this is your t-shirt. And what you're going to do is you're going to assemble it like this. So I put the colors where you stitch the thing. And you can see that around every point, it's a flat piece of cloth. A piece of cloth is flat. So around every point, you will have your 360 degrees, 2 pi, if you go everywhere around, except on this point, right? The point underarm will have if you go all around, if you draw a circle, you're going to have to go backwards and etc. You will find 3 pi, but everywhere else it's flat. But anybody who's looked at their clothes or their shirt will tell me this is not how we stitch t-shirts anymore. Why? Because this is a better cut. So that's how the better cut works. So this is just the sleeve, right? And you see that in your sleeve, you need some positive curvature. You need something like kind of positive curvature, because your shoulder is like this. Most of the time, this is how we stand. But then we would like also to be able to do these movements. So we need more room. So how do you get this room? You get this room with some positive. So here you get some positive curvature and some negative curvature, which is distributed along these blue seams. And how is it distributed? Why is it positive, negative curvature? Because if you go around the blue seam and you take a point and you try to turn around it, you see that if you turn around this point, you're going to get 2 pi. If you turn around this point, you're going to get 2 pi. If you turn around this point, here you're going to have pi, but here you're going to have less than 2 pi. There's this curve here. Now, if you go around the dark blue, you're going to have more than 2 pi here and more than 2 pi here. So if you go all the way, more than pi here and more than pi here, so if you go all the way around, you're going to have more than 2 pi. And this is what makes it that you can't lay your piece of cloth flat. This is the negative curvature. Right. So let me just go back to my dolphin, because as we all know, the sea is not infinite. At some point, if the dolphin is kind of low, you're going to hit the ground. When you hit the ground, your sound will travel, let's say, as on a flat plane, because for the moment, I know that the Earth is not flat, but for this argument, we're going to approximate the Earth by a flat piece. So again, turn my dolphins, and the sound is going to hit the ground, and it kind of hits a flat plane. And if I do the high dimensional analog of this map that was taking the upper half plane to the disk, here I'm going to find what we call a horrible, which is this is the missing piece of the sea that that's blocked by the Earth. And this brings me to a piece of very nice math that was made by Gromov when he was, actually Gromov did a lot of the hyperbolic formalism that I'm talking about now, even though the math was already there. I mean, dolphins were there before Gromov, right? But he explained how you can take any space, like for instance your flat plane that's very flat, and you can embed it more or less as horrible as I just said in a hyperbolic space. And he even gives an algorithm, and the algorithm goes as follows. You start with, say, just a flat, your flat piece of paper, and then you glue on it another flat, just a height 1, another flat piece of paper, but the distances shrink. Oh, no. So the distance shrink. At each level, the distance shrink. If I make another picture, at each level, I shrink the distance. And if I look at geodesics, now geodesics are going to have to go up because it's very fast to travel when you're up. And triangles are becoming thin. And if you think of it, you kind of see some kind of tree-like behavior in this, right. So a feature of hyperbolicity is linear isoperimetric inequality. So if you look at the Euclidean plane, you compute that you take a rectangle, a square, you will have that the area varies like the square of the perimeter. And this is no longer true in a hyperbolic setting. The area varies kind of like the boundary of your shape, always, no matter what you do. And this is summarized in this theorem, which I said Gromov mostly, but you know how it is, ideas, people. Anyway, I just summarized it because it's a nice summary of the feature of hyperbolicity. So the first one was hyperbolicity in the sense of thin triangles, as I told you. The second one is this linear isoperimetric inequality, which will be interesting in what follows. The third one I like because I wrote up with a collaborator of mine, Graham Niblo, is that the intersection of any two balls is almost a ball. Let me draw a little picture. If you're in your plane, you take a large ball and you intersect it with another large ball. Okay, bad picture, but anyway. So you're going to have something that's really long and thin. But if you're in a hyperbolic space, that doesn't happen. Each time you and I cannot draw a picture because I cannot draw something hyperbolic and something flat. But what's going to happen in the hyperbolic feeder setting is that when you intersect two, and you can think about with tree you can kind of draw that. You take two balls, you intersect them, you have something that still resembles a ball. And fourth point is that if you take a bunch of points, you can approximate and then you pull those points and you just look at the geodesic between those points, it kind of looks like a tree. And this is a reasoning that Groma's been using, that we use a lot as mathematicians. We do the reasoning on a much simpler object to see how we understand things, and then we try to take this same reasoning and express it in a more general framework. And then the fifth point, it's not really used in my talk, but I put it here because it was my first picture. In a hyperbolic space, what you do is if you take any ball and you try to project it on a geodesic, and by projecting is you're going to take any point here and points here, and you're going to look at the geodesics. And then you will see that the geodesic will do like this. It's more or less if you're in a city with a bridge. I think you have those type of behavior here in Bengaluru. There's like a small piece of, there's a little small place where you have to go. All right. So in infinite graphs, isoparametric inequalities are related. So this is a bit under the hood. This is where there's more math and I'm hiding a bunch of stuff under the rug. So in finite graph, isoparametric inequalities are closely related to the conductance, which is this formula which you don't really have to understand. I'm not expecting you to understand. I just put it here so that you have it. But this phi for a graph measures how difficult it is to cut your graph in two pieces. So for instance, if you have a graph that's like this, it's very easy to cut in few pieces, into two more or less equal pieces, but if your graph is like much more connected, then it's going to be harder. And so this quantity is very difficult to compute because it's anybody who knows a little bit of computer science, just by seeing the formula will say, yeah, that's impossible to compute. But you can approximate it very well. Computer, you can approximate it very well with a matrix and with something that is computable from the graph. And this quantity is going to measure the speed at which a random walk on a graph goes everywhere. So what's a random walk? You can think of a random walk as a drunk person going out of the bar, and he's drunk, so he doesn't know he's going left and then right and then so right. So it's going to or you can think of it as a bug on a graph, and that's going to go randomly to each neighbor. So depending on the geometry of your graph, the random walk will just stay at the same place, or it will go very quickly everywhere. And this is and how quickly it goes everywhere is controlled by this conductance. And here's an example that the picture I took from Wikipedia. So if you have if you take a random walk on Z, so you can make those are simulation, you can see that in the end it will go arbitrarily far. If you wait for long enough, it's going arbitrarily far, but it kind of remained closed in the beginning. So if your graph is this very wide circle, which it's kind of easy to cut into more or less equal pieces because you just remove two edges and you have two separate pieces, then your bug will take forever to go down there because it will go like this very long time, and then at some point eventually it will turn. So if you want it to go everywhere efficiently, you need to add shortcuts. So for instance, if you add this shortcut, like one more point, and then you link it to everywhere, that's one way in which your bug will very quickly go everywhere, but it's an expensive way because you've added a lot of edges. So that, depending on what you do, that could be a very expensive way to do things. So that's the question, how are you going to do it efficiently? So you're going to have to add shortcuts between very long, far away points. And the question is, can you do it with very few edges? And if you think in terms of hyperbolicity, adding those shortcuts is similar to this algorithm that Gromov gave, where you embed a plane in a hyperbolic space. So suddenly, so with this type of idea, with my collaborator Austin Lawson, we did some simulation about a French experiment. So what was the French experiment? French experiment was during COVID. As you know, we had COVID, everybody. So during COVID, in France we had a lockdown, meaning that a bunch of long distance travel was shut. We were not allowed to do this, not allowed to do that. And so I was lucky enough to be in Nice, and I live close to the beach, so I would go, I had the right to go to the beach. I would go to the beach, sit on the beach with my kids, and then one day I see a plane going by. And I was like, wait a minute. I thought we were not allowed to do that. So I went up and looked. And during the biggest of the lockdown, 90% of the long distance flights were canceled. 90% of the long distance travel was off. But it means that 10% was still on, right? And the question we had is, what is the effect of this 10% on how a random walk moves on my graph? So this is what we try to understand. So in order to understand that, we took this is the map of France. Each time I travel, I'm thinking I should do the same for the country I'm traveling in, and then I'm like, yeah, no, it's too time consuming. But I would love to do the same thing. In fact, I am in the process of doing the same thing on a world map. I mean, I'm not doing it. Some people who can actually code are doing it. So, okay, so this is the map of France, and we drew a graph out of it by just deciding that 8,000 people is 1 point, or that many thousand people is 1 point. So we put the point depending on the densities of the city, and we looked into. So this is where the science is kind of bad. It's really a heuristic. We just went online and looked how many passengers, and with that amount of passenger, we drew the graph and the random walks. So the first one, so you see that the first one is pre-lockdown, nothing happened, everybody travels a lot, and this is the lockdown. So this is under lockdown. So you can see that those few edges are still making quite an impact. And this is some kind of mild lockdown that we had after, and to me, it makes no difference. And below, this is a theoretical lockdown, which is you cut every single long distance travel. Not 90%, not 99%, but 100%. So it's theoretical. In real life, you never do it. And you leave, and in all those simulations, did leave the short distance all open because otherwise we couldn't do the simulation. That was really a technical. And here you can see that with the theoretical lockdown, the entry point of your random walk or your virus just stay wherever they are. They go nowhere. They could, if you wait for long enough, it'll go everywhere. But you really have to wait for a very long time. Whereas if you add a few of those long distance edges, it goes very quickly everywhere. And we did the same type of simulation with a replicating random walk, meaning that at each step you become 2 or 3. And you can see that the theoretical lockdown where you really close everything, this makes a difference. But as soon as you leave some 10% open, it does make a big impact. And right, so here we even see. So those are the computable value from the graph, this lambda 1. Right. So that's more or less the math I wanted to talk about today. And I'm finishing with a tree, which was the tree that I drew. And unfortunately, our trees are having trouble because of a climate crisis that we all have heard about. And I want to say a few words about this, because when I was the kid's age, we had an ozone hole, and everybody was talking about the ozone hole, and miraculously, the several governments took a few measures, and the ozone hole disappeared. So 10 years ago, it was like, yeah, it's going to happen the same thing with climate change. And it doesn't seem to be happening that easily with climate change and the climate crisis in general. So it's much more complicated because we talk about global warming, but the truth is it's not really global warming the problem. If we added 1 degree to every single temperature we have, it wouldn't be such a big deal. The problem is that if you want to have a 20-degree, for instance, average, instead of having 21, 21, 21, what we're going to have is 15, 25, 10, 30. And this is what makes life much harder. We would have a we know what the solution is. The solution is that all the fossil fuels should stay underground, and keep the carbon trapped underground. Except that this is impossible to make. Every solution we find, like solar panels, they ask us to dig some more stuff out of the ground, which is not carbon, but which is other stuff, and which then in turn threaten biodiversity, for which we don't have a good measure to understand what is the problem, what we should do, and we tend to not agree on what we should do. So I have no solution. I have no advice. I mean, yeah, I have an advice. The only advice that I would like to give is try to learn about the facts, try to question the facts that you hear, and that's basically the only advice I can give, because I'm here traveling and basically promoting a non-sustainable lifestyle. And the problem, if you think about it, the problem is largely due to the West, to white men, to be honest, because carbon emission is very correlated to money. And most of the money is concentrated on white men, although Indians are now catching up, and Chinese too. So if I have to conclude, I would conclude with a quote by Mahatma Gandhi, who said, "Live as if you were to die tomorrow." And when I say live, you really should live with important thing, and what's important is really communication and people and not material stuff. And learn as if you were to live forever, meaning learn whatever you can about these things. And that's the end of my talk. But before I finish, I would like to, this is because this was unexpected, so it's not in my talk. This is a very nice way of producing, which I didn't know, which was produced by this very talented young person. This is a feature of hyperbolicity, because if you draw a triangle, forget about the wrinkles. If you forget about the wrinkles and you draw a triangle, you will see that your triangles, if you think you do that at infinity, you will see that your triangles is going to be thin. And this reminds me that I had something here that I wanted to show you, that I made especially, but I don't have enough for everybody. I think I'll give one to this very talented young person. Those are handkerchiefs. Those are hyperbolic handkerchiefs. So if you understand what I said today, if you use them to blow your nose, most of your snot is going to be near the boundary. So if you like your snot to be inside the handkerchief, you need a flat one. If you don't mind your snot being distributed near the boundary, you can use a hyperbolic handkerchief, and you can pass it around to see the curvature. And I will stop here. Thank you very much.
Just that in space-time, when we have a big mass and the space-time curves, does this hyperbolicity apply to that geometry? The Einstein's thing where the space-time curves, and it is not flat, and we have a curve there. Will this hyperbolicity apply there?
I don't know enough of space-time to give you a good answer. I think the answer is no, because within space-time you have space, and space is flat, and the time will not deform the space, I think. So I think the answer is no. You will have, I think you have some hyperbolic features, but it's not overall hyperbolic. You will find thin triangles, but you will find flat triangles as well.
Yeah. Now, can I add a comment to that?
Maybe you know better than me. Yes, please.
No, not better than you, but I just want to say that if you take the pseudosphere, which is the space of negative curvature, it sits very nicely in the Einsteinian space, Lorentzian geometry, where the distances are measured with a minus sign for the time and a plus sign for the space. And that space, just like you write x squared plus y squared plus z squared equal to 1 on the sphere, you put x squared plus y squared minus t squared equal to 1 or minus 1, I don't remember, then you get a shape which is exactly the disk that she was talking about, where the straight lines are circles and things like that, in a certain way of looking at it. So it is connected to relativity.
Questions?
So when you talked about that particular map, that z is getting mapped to iz plus 1 divided by I plus 1, in the hyperbolic space, we don't have that certain notion of measuring angles, right? So how can we show that that angle is getting preserved in that mapping?
So you in the hyperbolic plane, you do have a way of measuring angles, but in the general hyperbolic space, you don't. But, for instance, in a graph, you don't necessarily. But in the hyperbolic plane, as I described here, you do have a notion of angles because it's a manifold. So it has if you're a bug on the hyperbolic plane and you have a very tiny vision, you're going to think that you're in R2. And so locally it's R2. So locally you can measure angles. And that's your measure of angles, yeah.
And by that measurement of angle, we can certainly show that angles are preserved in that manifold.
Yeah, exactly. Yeah.
Okay.
Yeah, and that's this notion of angle that this map preserves. Yeah. Yeah, you have a notion of angles. If you have a manifold, you kind of have a notion of angles because then you approximate it by Rn, and there you have angles. Yeah, you can have angles if you have an extra structures. You get angles if you have an extra structure that kind of make your space resemble locally to Rn, then you can find angles. Right, exactly. Yeah. So the hyperbolic plane is really the model that Gromov got inspired from. But the hyperbolic plane is really something very concrete that mathematicians have been studying even way before Gromov. And yeah, and on which you have much more structure because you're in C, because you have much more structure than you would find, for instance, on a graph, but you have similar behaviors in graphs, in some graphs.
Hello ma'am, I thoroughly enjoyed the talk. Geometry as a whole is a subject that requires a lot of imagination, and you should be able to visualize the shapes and all that. So, but hyperbolicity, as a separate branch of geometry, how can one study hyperbolicity without the clear imagination and realization of those curves?
I don't know. I do my best to try and but most of the time, the way we do is we understand things on trees, and on trees it's a graph, so you can actually see things a little better, and then this is where the math skills really come in. You have to translate whatever you understood on trees in this more general framework of a metric space that doesn't need to be a tree, that doesn't need to have angles, that can be a bit.
Yeah, I mean, the reason I asked the question was when you're thinking about a rectangle, a rectangle has length and a breadth, and the area is L into B and perimeter so and so. So, but when you're talking about hyperbolicity, this kind of realization and imagination is non-existent. So when we're solving a question, for example, or at least when you're thinking about it, how to go around it, because there's nothing going on in our heads. The shape isn't there.
Well, I think that mostly what we do is we discuss with other mathematicians, and they have their vision, and you have your vision, and you try to match it. And then in the end, you have to write a math paper where everything holds to peer scrutiny.
Thank you,
But
ma'am.
yeah, every time I read a new math paper, I try to really understand everything, but I keep thinking, you know, this is correct with some statistic, some percentage. You never know. Mistakes could happen.
Thank you, ma'am.
Hi. There was a slide over there that mentioned if we go around a point, it's more than 360 degrees.
Yeah.
I wanted to know why that happens.
Well, so I'm thinking if I have a good way of explaining it to you without. Yeah, I guess. Yeah. But the hyperbolic handkerchief, you could see it because of the way I did it. But in the model of the hyperbolic plane is really a computation that you have to make. You can pass it around. But yeah. In the case of the hyperbolic plane, it's really a computation that you can make by taking a circle and measuring everything. Yeah.
So it's just an empirical measurement based thing. Like
Yeah.
There's no intuition behind why that happens.
There must be one. I don't have it right now to give it to you. Yeah. Yeah.
What does the circle look like?
It still looks like a circle. Yeah. So in the hyper, that's kind of surprising. Circles still look like circles in the upper half plane model, except that the centers are not where you think they are. So if you're in the upper half plane model, if you want to draw a circle, it'll still look like a circle, except that the center is probably going to be somewhere here. But they still look like a circle.
I have a small comment about her question that, if you want to visualize that greater than 360 degrees, probably it's a good point to look at the hexagonal, the tiling, and see how the triangles will fit in there. So there probably one, with some, intuitively at least, one could be able to see why you will get greater than 360 degrees. The tiling of the plane, the hexagons.
Okay.
Yeah.
Any questions?
Are there any online questions? So if there are no further questions, I request Roshni to present Indira with a small memento of this talk.
Thank you very much.
And let's thank the speaker for a really wonderful exposition of the subject. And let's meet outside for coffee. And if you have further questions, we can discuss them over coffee.
Thank you.